Hello and welcome back to Ubad's lab. Today we're going to be explaining how the Heisenberg uncertainty principle arises naturally from looking at the commutator and some simple linear algebra. So to do this, first we're going to be proving how if two operators commute, then they share an eigenbasis set, and if they don't commute, then they don't share an eigenbasis set, which isn't obvious at first, but understanding this is going to help us gain a better conceptual understanding of Heisenberg's uncertainty principle. So first, to do this, we're going to make the assume A and B commute, which is the same thing, which written here is the commutator is equal to 0. It's another way of saying it commutes, that the two operators commute, A and B. What is the definition of the commutator? It's A, B minus B, A. So it's the difference of the two operators switched around. And we're saying that this is equal to 0. Now this is the same thing as just saying that A, B is equal to B, A. Now what is this telling us? It's telling us that the order of performing these operators on a wave vector doesn't matter, whether you do A first or B first. We're also going to assume that A operated on the ket psi gives us A psi, where A is a scalar, a constant. This is saying that psi is an eigenvector of the operator A, and now what we're going to try to do is show that psi is also an eigenvector for the operator B. Then that's going to be our proof for showing that they share an eigenbasis set. So let's use our first assumption. A, B, psi is equal to B, A, psi, since from our first assumption, AB is equal to BA from here. Now let's use our second assumption. We see that A operated on psi is appearing here, and we know that it's equal to A times psi with the constant. Now we're replacing with the constant A, psi. Now this is just a scalar, a constant, so it can be brought out to the front. Now what are we seeing here? You may notice that this B psi is appearing on both sides here, and we have our operator A, and we have a scalar in the front. What does this look like? It looks like an eigenvalue equation. So we know that B psi is an eigenvector of the operator A, but we were given that psi is an eigenvector of the operator A. So what B has to be doing is it has to be just scaling the vector psi by a certain amount. In other words, psi is also an eigenvector of the operator B. So any eigenvector of A is also an eigenvector of B. This tells us that they share an eigenbasis set. This is very useful, and this is very useful to understand. It's going to help us explain uncertainty. It can also be shown that if the operators don't commute, then they don't share an eigenbasis set. All right. Now we're going to use this and look at a physical example. It's commonly told that quantum mechanics isn't intuitive, so a lot of times it's not useful to look at physical examples. But I think just looking at simple examples can be very useful. So what we're going to look at is a particle traveling here, and there's 3 slits that the particle can go through. So you may have heard of the common double slit experiment. This is the triple slit experiment. And so the particle can go through either slit 1, slit 2, or slit 3. and so it's quantized. It's in a, once it collects over here and it hits a wall on this side, all we know is that the particle went through a superposition of traveling through slit 1, slit 2, and slit 3. We don't know for sure which one it went through. But once we put a detector here, let's say we have a detector that's kind of watching which slit it goes through, then the wave vector for the slits collapses onto a certain slit. So then we know, for sure which slit it went through. So let's represent this with wave vectors, with an eigenbasis set of vectors. Let's have the A1 ket represent slit 1, the A2 ket represent slit 2, and the A3 ket represent slit 3. And without taking measurements, our wave vector, which represents our particle, is in a superposition of the 3 states. We don't know which slit it went through. It goes through a mixture of the different slits. But once we make a measurement on which one it went through, the wave vector then collapses onto a certain state. So let's say that we know for sure that it went through slit 2. Then our new wave vector collapses onto this state. This is the Copenhagen interpretation with collapsing wave functions after experiment. So this is our new psi. Okay? So now let's undo that. And let's introduce another property, another quantized property. For simplicity, we're going to introduce another quantized property of energy. Let's say that the particle can have 3 different energy states, B1, B2, and B3. These are 3 possible energy states the particle can be in. And we're just going to assume that the energy and which slit the particle went through, those observables, they don't commute. So if you measure one and then you measure the other, your answer is going to be different whether you switch the order of your measurements. So assuming that, from our proof earlier that we did, if they don't commute, the operators that represent, the operator that represents energy and the operator that represents which slit it went through, if those don't commute, then they don't share an eigenbasis set. So let's make a eigenbasis set for energy. B1, energy 1, B2, and B3. And you see, I tilted it a bit. This is because it can't be the exact same eigenbasis set of what slit it went through because the operators don't commute. Okay, so now we have this wave vector. It's in a superposition of energy states and it's in a superposition of slit states. Now let's see if we make a measurement on the slit again, which slit it went through. So let's say it collapses again onto 2. Let's say we know for sure it went through slit 2. And the wave vector is going to collapse onto slit 2. Now it's here. What happens here? We know for sure what slit it went through, but now it's in a superposition of energy states of B1, B2, and B3. It's in a mixture of these different energy states. We don't know for sure which one it went through. Now, you may see where I'm going with this, but now let's make a measurement on which energy state it went to. Let's say after taking a measurement on the energy, we know for sure that has energy corresponding to the B2 vector. Then from here to there, our wave vector is going to collapse onto this energy state. Now our ket is here. Now what happened? Our wave vector is in a superposition of slit states. Just we took this measurement right after taking our measurement of what slit it is. And now now we don't know which slit it's in. It's in a mixture of slit 1, slit 2, and slit 3. So just from making a measurement on the energy, it's immediately giving us uncertainty in what slit it went through. And we can repeat this back and forth and keep on going back and forth, and we'll keep on having uncertainty in the other, just from making a measurement in one of them. Intuitively, this doesn't make sense why taking a measurement of one thing is going to affect your certainty in another thing. But looking at it this way with vectors and commutators helps us get a better insight into it. And it's interesting how a simple mathematical object, the commutator, can lead to a better understanding of Heisenberg's uncertainty principle. And the way Heisenberg looked at it was, it's commonly shown with position and momentum of a particle. So just replace the two properties that we looked at here with position and momentum. The more certainty you have in, let's say, position, the more uncertainty you have in momentum. And you can see from this example how that's arising.